All right, now we want to use our knowledge of dipole of dipole molecules to talk about intermolecular forces. These are the forces of attraction between molecules. They're the forces that are very important in describing not only a lot of biology, but they're also the force that answers very simple and basic questions like, why does a liquid stay a liquid? I mean, have you thought about it? We know water molecules, that water is a collection of individual molecules of two hydrogens attached to one oxygen. But in order for them to exist as a liquid or a solid ice, there has to be some force of attraction that one water molecule has for another. Otherwise, they'd all fly off and go their separate ways. But you can see very clearly, particularly with water, that when you spill liquid water on the desk, what happens? Does it suddenly disappear up into the atmosphere? No. It may spread out, but the water molecules are still close together. There is a force of attraction between those molecules. Intermolecular forces are the forces of attractions between molecules. We're going to divide them up into 2/3 general categories. The first of these categories is dipole-dipole I can't spell action today, is dipole-dipole interaction. And it's the force of attraction between two dipoles or two polar molecules. The other type of intermolecular force is London dispersion, which is also known as a induced dipole. And if I tell you what that means and what that is, then I'll have done the entire lecture right now. So let's hold off on London dispersion for just a second and focus on those dipole-dipole interactions. All right, so let's take a look at dipole-dipole interactions. And it's the force of attraction between two molecules, let's just use the term dipoles, between two dipoles. The classic example of dipole-dipole interaction would be the attractive force between molecules of hydrochloric acid. Hydrochloric acid is a linear molecule with hydrogen, you'll remember, has an electronegativity value of 2.1, and chlorine has an electronegativity value of 3.5. So their difference is 1.4, which makes it a very extremely polar molecule with a partial positive charge on the hydrogen and the partial negative charge on the chlorine. Every single molecule of hydrochloric acid exists in that duality, with that partial positive over the hydrogen and that partial negative over the chlorine. Well, we know that full charges are attractive to each other. We saw that at work in ionic compounds. We know that opposites attract. The same is true for partial charges. The partial negative charge on this chloride ion, well, the partial charge on the chlorine here, the partial negative charge on the chlorine is attracted to the partial positive charge on the hydrogen of a different chlorine molecule, right? We're in two different hydrogen chloride molecules. Then partial negative charge on this hydrochloric acid molecule is attractive to the partial positive charge on that hydrogen in this different hydrochloric acid molecule. Come on. There we go. This force of attraction between these partial positive and partial negative charges is known as dipole-dipole interaction. And things stay liquids or stay solids because of this attractive force. It's what keeps this molecule of hydrochloric acid from drifting away into space away from that molecule of hydrochloric acid. So dipole-dipole interactions are very important. Couple important things to note is that the strongest dipole-dipole interactions are more than 2,000 times weaker than a typical covalent bond. So the force of attraction in a dipole-dipole interaction, this force of attraction is much weaker than this covalent bond. And that's an important thing. Why? Because when we add heat to a substance, we want it to boil, not break bonds, right? When we add heat to our hydrochloric acid, we want our hydrochloric acid to boil or enter the gas phase, because the weak dipole-dipole interactions are being overcome instead of the stronger covalent bond. So these dipole-dipole interactions, or these intermolecular forces, are much weaker than your intramolecular forces such as covalent bonds. Now there is one dipole-dipole interaction that's extremely strong and is so strong it gets its special name. And that's hydrogen bonding. If you've had any chemistry before, or if you've had any biology, you've probably heard people talk about hydrogen bonding. Hydrogen bonding is just a special form of dipole-dipole interaction It's a special form of dipole-dipole interaction where the dipoles involved are the result of three important types of bonds, of hydrogen bonded to nitrogen, hydrogen bonded to oxygen, or hydrogen bonded to fluorine. In order to have hydrogen bonding, the dipole-dipole force you're talking about has to be the result of hydrogen bonded to nitrogen, hydrogen bonded to oxygen, or hydrogen bonded to fluorine. There's no effing way you should forget it. Get it? No effing way you should forget it? No nitrogen, oxygen, fluorine? No. Seriously, hydrogen bonding only results when hydrogen is bonded to one of those three atoms. If you don't have that hydrogen-nitrogen bond, that hydrogen-oxygen bond, or that hydrogen-fluorine bond, you can't have hydrogen bonding. The classic example of hydrogen bonding that everybody's familiar with is water. Water has a dipole with a partial positive charge on the hydrogens and a partial negative charge on the oxygen. And this dipole is indeed the result of a hydrogen-oxygen bond. And water molecules are kept together via the force of attraction the force of attraction between the partial negative charge on the oxygen of one water molecule with a partial positive charge of the hydrogens of a different water molecule is referred to as a hydrogen bond. Hydrogen bonds occur not only in water, but they're very important in our everyday life, particularly in proteins. Protein folding occurs primarily as a result of hydrogen-hydrogen bonding, as well as some other bonds, but resulting in the folding, not the chain, but the folding, before you come and curse me back after you've had 150. Hydrogen bonding occurs whenever you have hydrogen bonded to nitrogen, hydrogen bonded to oxygen, or hydrogen bonded to fluorine. Another everyday molecule you're familiar with that does hydrogen bonding would be that ammonia we talked about. Partial positive charge on the hydrogen, partial negative charge on the nitrogen, that force of attraction between these two is a hydrogen bond. Chemistry's easy, life is hard. That's a hydrogen bond. Okay. In covalent compounds, polar molecules exert attractive forces called dipole-dipole interactions. So, let me phrase that another way. To have dipole-dipole interaction, you must be a polar molecule. In other words, you must be a dipole to have dipole-dipole interactions. We call a special case of this dipole-dipole interaction where hydrogen is bonded to fluorine, hydrogen is bonded to oxygen, or hydrogen is bonded to nitrogen as hydrogen bonding. And this is the force of attraction that plays a major role in everything from DNA to proteins to just our typical aqueous environment. So that's polar molecules. What about nonpolar molecules? After all, nonpolar molecules exist as liquid. Oil is nonpolar, but we've all seen with our own eyes that oils exist as liquids. All right, let's talk about London dispersion forces. London dispersion forces are the primary force of attraction between nonpolar molecules. We know nonpolar molecules have to have some sort of attractive force. After all, oil is a nonpolar substance, and we know that oil molecules are capable of staying together and being attracted to each other in order to form a liquid. Right? Most of the oils we're associated with in our everyday life are liquids. So there has to be some sort of force of attraction between nonpolar molecules. That force of attraction is London dispersion forces, otherwise known as induced dipoles or temporary dipoles. To understand what occurs, we have to think about how we view the atom. We view the atom, remember, as a huge electron cloud with a tiny nucleus. Now, this electron cloud is not a rigid, set-in-stone structure. It's more like one of those stress toys where it's like a thick rubber balloon filled with the sand. You know, when you squeeze one end of the thick rubber balloon and the other end pops up big, and then you squeeze that end and the sand shifts the other way and pops up big, or you squeeze the middle and the sand goes out to the two sides and forms a new shape, and then finally you get so stressed you put your fingers through the rubber balloon and the sand goes everywhere. Anyone? No one's had one of those stress toys? All right. Of course, you guys don't have stress, because whenever you do, you can just turn on one of your chemistry lectures and relax. But at any rate, if we view electron clouds as something soft and deformable, we can see how dipoles would be induced. I've got my atoms. They're small positive nucleus surrounded by their electron cloud that has a negative charge. Well, like charges attract, but opposite charges repel. So if these two atoms, nice along in their normal shapes, are brought close together, come together right now, if they come in close proximity of each other, then you have two negative charges coming in within proximity of each other first. And like charges repel each other, even electron clouds. So the electron clouds are going to distort in order to minimize that electron repulsion. So we go from having an atom shaped like that to having... Get away from me! And when that atom distorts, it shifts the charge density of the atom. And what it does is it creates an area where the electrons have sort of left that has a partial positive charge, and where the electrons have sort of shifted, they have a partial negative charge. Now, it's important to note that even though we're using the same partial charge symbols as we do for a dipole-dipole, the partial charges for London dispersion are generally, but not always, but generally are a little bit weaker than your typical dipole-dipole interaction. So you see that distortion in one atom. Well, it's not just two atoms that are coming together in too close proximity. Lots of atoms are coming in too close to proximity of each other. So at the same time that atom's distorting, guess what? The atom next door to it's distorting and creating its own area of partial positive and partial negative charge. And the force of attraction And the force of attraction between these temporarily induced dipoles is referred to as dispersion forces, or London dispersion forces. So, to kind of encapsulate here, London dispersion forces are the forces produced by atoms moving close to each other, or the electron clouds of molecules moving close to each other, causing temporary changes in electron density, resulting in partial positive and partial negative charges, which in turn cause those partial positive and partial negative attractions to be attracted to each other, which is what we refer to as London dispersion forces. Now, a question I want to ask: do all molecules have electron clouds? Yes, they do. And if all molecules have electron clouds, can they be distorted? Yes, they can. So, all molecules have electron clouds. So all molecules can have London dispersion forces between their molecules. However, because most dipole-dipole interactions are stronger than most London dispersion forces, London dispersion forces are not the primary intermolecular force between dipoles. Dipole-dipole interaction is. London dispersion is the primary force between nonpolar molecules, though. All right. All molecules have electron clouds, so all molecules have London dispersion forces between their molecules. Because most dipole-dipole interactions are stronger than most London dispersion, London forces are not the primary intermolecular force between dipoles dipole-dipole interactions are. London dispersion is the primary force between nonpolar molecules, however. All right, that summarizes it. Now let's check ourselves before we wreck ourselves. Real quickly, the stronger the intermolecular force, the higher the boiling point, and the higher the melting point. Ionic compounds have extremely high melting points because ionic bonds, as a general rule, are stronger than intermolecular forces. Because dipole-dipole interactions are stronger than London dispersion, dipoles have higher melting points than do nonpolar molecules that have to rely only on London dispersion. And you can see that in this chart over here. If you look, you have hundreds and thousands of degrees Celsius in order to melt an ionic compound, whereas water melts at 0 degrees and ammonia with hydrogen bonding at -78. Dipole-dipole interaction, -89, -15, right? Strength increases this way. Then our weakest are London dispersions, -100 and -220, right? The stronger the force, the higher the melting point. And I know a couple of you are already pointing out the exceptions here. And this would be an exception. This would be the case where the London dispersion between these two appears to be stronger than the dipole-dipole between those two. Go figure. Identify the main type of attractive force that are present in the following liquids: ionic, dipole-dipole, hydrogen bonding, or London dispersion. Well, typically we'd start by drawing our Lewis structure. But our nitrogen trichloride, your bond is between nitrogen and chlorine. Go ahead and look up the electronegativity values. You'll discover that nitrogen is 3.0 and so is chlorine. So 3.0 minus 3.0 is 0. So they're nonpolar. So that's a nonpolar molecule. So your primary force is going to be dispersion. Whenever you have a nonpolar molecule, your primary force is dispersion. Water, you have oxygen bonded to hydrogen. So hydrogen bonding would be your primary intermolecular force. You have an element bonded to itself, so there's no electronegativity difference. So it's going to be nonpolar, which means that the only possible intermolecular force is London dispersion. Potassium is metal, chloride is a nonmetal, so you have an ionic compound. Ammonia, you have nitrogen bonded to hydrogen, arrows that don't cancel out. So H bonding is your primary intermolecular force. And that's all there is to it. Chemistry is easy, life is hard. Why don't you write down Prometheus? Write down Prometheus. Last thing you're going to do in this lecture is write down Prometheus.